So the second talk, you'll be talking again about MPC-based solutions, so secure multi-part-based, secure multi-part computation-based solutions for machine learning. And you have heard a little bit about it in the talks yesterday and today already. And on this one, I will be focused most on stuff that can be done there, other than neural networks, other than training or inference of neural networks. So just a brief recap of what was told yesterday and today. The scenario that we are using secure multi-part computation to essentially get rid of trusted third parties. So if we had the trusted third party, we can just forward all the data to this trusted party that does the computation, give us back just the result, right? But I mean, that's a very, very strong assumption. We don't want to have such kind of trusted third party. So we just run some MPC protocols to eliminate the need for the trusted party. Yeah. Okay, in the scenario that we are in, we are mostly focused on the case of outsourced MPC computations. So, and we are using secret share-based MPC solutions. So what happens is the following. The data owners, they are going to generate the secret shares. I mean, they first convert the real numbers to the modular representation. I mean, I talked a little bit about it yesterday, and there were other talks also about it. How this normally represented, so normally use fixed point representation kind of things. And okay, so the data owners, they convert to this modular representation, then they secret share the values, and they give the secret share values, the shares to the servers that will be doing the computation. It's outsourced computation, as I mentioned, so maybe there will be 3 or 4 servers doing the computation. And then in the second stage, these servers that are the computing parts will do some computations over the secret shares, and they will not learn any information about the underlying data. But then in the very end, once they achieve the result of the computation, they will essentially just reconstruct the secret shares towards whoever is supposed to get the output of the computation. Maybe the data owners are the ones that are supposed to get the output of the computation. Maybe it's one of the servers that will hold the model for further applications in the future, and so right. So that's the setting that we are considering normally. Okay, and as I mentioned yesterday, in principle, we can represent functions by using multiplication, addition gates, and we can compute anything using this or using like undershore gates. I mean, they are compute gates, set of gates, right? But I mean, would you do that? Would you just like pick any circuit representation and try to implement it? That would be very, very inefficient, right? So, I mean, if you want to get efficient solutions, normally you want to optimize as much as possible things, and especially some of the important building blocks, like things like secure comparison or secure linear algebra operations. They are used over and over. So you normally want to optimize those building blocks so that you have a better solution for them, instead of picking any representation, any secret representation of these operations. Okay, but okay, so there are some optimizations that we can do at the MPC, pure MPC level by the representation that we're using for the building blocks and so on. But on the other hand, I mean, we also need somehow, and that's something that the previous speakers have talked a little bit about as well. We need to make the machine learning algorithms that we are trying to implement a little bit more MPC friendly or FHE friendly, whatever technology you are trying to use, right? I mean, there are many choices that people make whenever they implement machine learning in the clear. Sometimes, like the difference between one option or the other, they are very marginal. But since the cost to implement in the clear, it's minimal, they choose the one that it's maybe a little bit more expensive, but it gives a little bit of more accuracy or something like that. But whenever we change like the computational model or cost model here in MPC or in FHE, it's very different from the cost model that we have for in the clear computation. So we somehow have to reanalyze what are these kind of trade-offs. If you really want to make some choice that maybe you will make your solution like 10 times slower and give you a very marginal gain in accuracy. It's a question that if you are trying to implement some privacy-preserved solution, you have to deal with. Like the trade-offs between accuracy and running time and all this kind of things. So a lot of times we will have to work to make all the machine learning techniques more MPC-friendly in the case that we are implementing privacy-preserved machine learning using these based solutions. Okay, so I mean, the solutions based on MPC for machine learning, they are very active research area. You have saw some results that were presented yesterday and today already, but I mean, there are many papers around being published in the recent years for things like training and scoring of neural networks, linear regression, training of tree ensembles, and so on. And also, like, it's not the case that the underlying MPC schemes, they are set in stone, and it's a field that is not evolving anymore. Actually, in the last decade or so, there were a lot of developments in the underlying MPC schemes. So the technology that goes in the solutions, the MPC technology that goes there, it keeps evolving. Like there are new schemes that improve efficiency for some settings and so on coming up all the time. And I'll show one of them that, for instance, I think it's from 2 years ago, for instance, on the underlying MPC one. So some of the things that I'll be talking a little bit about today is the following. So a lot of papers that you see out there, you think about privacy preserving training of machine learning models, right? But a lot of times these solutions, they assume essentially that the data that you need for the training is ready for consumption, right? The data is there. It's not all owned by the same part. Maybe it's distributed among many parts, but it's essentially ready for consumption. So you can just do whatever training method you want to do, and you're good to go, right? But if you look like at the pipeline for data scientists, what they need to do, like whenever they are training and trying to make ML models better and better, training is not the single part of it, right? Indeed, if you see like surveys, you see data scientists will normally say that the time that they spend during training, it's the minority of the time, their working time, I mean. So things, there are a lot of other things that need to happen, right? So if you have a data set, a lot of times you need to clean your data set. You need to pre-process your data set. Also, I mean, the data that you get is not like perfect with all values, of the features being with values. So there will be some missing values for some features in some instances and so on. Also, a lot of times you get continuous data, and depending on the solution that you are using, you need to discretize the continuous data, all these kind of things, right? Also, a lot of times you don't want to use all the features of the input data that you have, because there are some features that they're not so relevant. There are other features that they are more like, they improve more your model. So you want to do like feature selection or feature engineer sometimes. So all these kind of things that go on other than the training itself. And even once you are done with the training, you have to validate your model. You have to fine-tune your model, right? So, I mean, the cycle of training a model and maintaining the model, all this machine learning pipeline, it's not only about training, right? I mean, there are many steps that need to happen in there. I will talk a little bit about some of these steps, especially like for features. How do feature selection in a privacy-preserving way? Because if you think about it, okay, we have these solutions that do the privacy-preserving training in a private way, but what is the meaning of that? If to begin with, you have to do feature selection or some of this pre-processing in a non-private way. What is the relevance of having the training part in a private way if you have to review information for the pre-processing? I mean, And if you really want to have a pipeline for realistic deployments, then you need to cover all the steps of the machine learning pipeline, right? So the stuff that I will be talking about today, it's essentially coming from these two papers that I was co-author. One appeared in ICML 2 years ago, and the other one in PETS last year. You can check the details in the papers, but I'll try to give an overview of what is going on here. So the first thing I'll be talking about is about MPC-based protocol for privacy-preserving feature selection. And this one that I will be presenting is essentially based on the filter method, which is a method that's independent of the training. So the filter method, you pick the original features, you compute like scores for every feature that you have in your data set, and then you select some of the features according to the scores that you computed for the features. And then instead of using all the features, you only use the most relevant ones, according to the rank that you have computed. And there are many methods that can be used for computing the scores, and the one that I'll be talking about, it's essentially like gene input. It's one that, I mean, whenever you see like MPC-based implementations of these things, the gene input, it's more MPC friendly than other techniques like mutual information or Pearson correlation. So as I thought, like some of these techniques that they have comparable performance in the clear. Whenever we turn to privacy preserved solutions, the computational cost of these things are very different. So there are trade-offs there. So we essentially show that we can do like feature selection using this combination of gene input for scoring, and then the filter method for selecting the features. And this can improve like the performance of training methods for real-world data sets. I mean, we picked, of course, the data sets before we started the experiments. Of course, I cannot rule out that this kind of techniques will be perfect for all kinds of data sets, but there are many relevant real-world data sets where it works completely fine and very well. But there should be contraexamples there, I'm pretty sure as well. Okay, so what is this feature selection? Let me try to put some terminology here. So we have some data set S, which will have some set of training examples. So you have M training examples, and training examples will consist of some features, so X1 up to XP, and some label Y for each training example, right? And we'll consider here that for the label we have N possible classes. But we don't want to use all these P features for the training of the machine learning model. We want to select some subset of the features to make more accurate models. As well, like if we do the training part with less features, the efficiency of the training part will improve. So it can improve both accuracy and the training time by doing some feature selection. So as I mentioned, like in the future filter approach for feature selection, essentially you first compute on one score for every feature. And this score will essentially like indicate how good or not that feature is for predicting stuff. And then you only pick the best scoring features for to retain and do your computations of the training part. And there are many techniques that you can use for this scoring, and like Pearson's correlation coefficient, mutual information, gene input, and so on. And the one that we will be working with is gene input for efficiency reasons. Okay, so what is this gene input? So if we pick some feature, I mean, if we pick one feature and we check how the values that that feature can have, like let's say that we have a feature which is age, and the age can range from 1 up to 100. And then you can essentially define based on the values of this feature a partition of the data set. So you pick the sets, pointer here. I don't have a pointer, but we pick some sets S1 up to SL, which will be a partition of the original data set. And now, how do you compute the gene input? I mean, it's a standard measure in math and economics. They use a lot the gene index and so on. So essentially, what the computation that you do for the gene input, you pick for every set of this partition. This will be the summation over all possible class of the probability that one handle sample for that set of the partition falls in that class times 1 minus the same probability. So if you just like work the terms here, it's essentially 1 minus the summation over all the possible class of the probability of randomly selected instance of the set being that class that you're considering. So I mean, the smaller you have the gene index, the gene input, the more homogeneous is the set in the sense that it will fall like pretty much all in the same class. So it's more like useful. And then, but just for every set of the partition, right? But if you want to have compute the gene input of the feature, then you have to average over all the sets of the partition. So essentially, you do the summation considering the size of the set compared to the total samples, number of samples, and then the gene input of the set. Okay, so in principle, like this gene input, it's essentially an estimation of the likelihood that if you randomly pick an instance, what is the chance that that instance will be misclassified based on the knowledge that you have only about that feature? So the smaller that you have the gene input of the feature, the smaller the chance that you misclassify based on that feature. So you want to have like smaller gene scores for the features. And then the idea is that during feature selection, you just keep the K features with the lowest gene scores. And there are the ones you don't bother with for the training. So, okay, so all these things that I was talking about, it's essentially about discrete variables, right? But what about continuous ones? And it becomes more tricky, right? So for continuous ones, normally what you do, you would sort all the feature values, and then you try to determine the candidate split points for the feature range in order to obtain the optimal one. So what is that something that you really want to do in the setting that you are running this on top of MPC? Not really. I mean, sorting MPC is very expensive. So what we did instead, I mean, so just the kind of considerations that we have to take care of whenever we are doing this secure implementations, because in the clear you can do all these operations, they are the same. They are very cheap anyway, so you don't care about the cost, the computational cost, but whenever we are doing the computation in a secure way, then the costs become much higher, so you have to make decisions. So one thing that works very well in practice and that improves the computational cost a lot. Okay, so instead of doing this sorting and trying to find the optimal splitting point, we just decided, okay, what about we just pick the mean value of the feature and we use that point to do the splitting? Would that work well? And it turns out that in practice, the accuracy that you get by doing feature selection with this mean split gene score is essentially on par with the traditional gene score. So, and you are saving a lot in terms of computation. I mean, I'm not saying that this will be on par for all data sets, but as I mentioned before, we picked some data sets before starting this, and we did experiments, and for many data sets, this would work very well and be on par with traditional gene score. Okay, so it's essentially like the accuracy that we are getting is essentially on par for these data sets, on par with the traditional gene in position one, or some correlation or mutual information. And it's an improvement, of course, when you compare to just doing the training on the raw data set without doing some feature selection. Okay, so what about the adversarial model that we are considering here? I mean, our protocol is sufficient generically that we can run on top of pretty much any MPC scheme. Even if it's like dishonest majority, honest majority, whatever, the protocol is sufficient generically to run on top of it. I mean, you just have to change the underlying MPC scheme. But the set that we consider like for efficient reasons was the following. So for semi-honest adversaries, we consider the protocol by Rappe et al. It's one of the fastest MPC for semi-honest from CCS 2016. So it's essentially assuming that you have 3 computing parts, at most 1 corruption. And I mean, this setting is used quite a lot in PPML based on MPC. And we also evaluate in the same setting, like 3 computing parts, 1 corruption with malicious adversaries. But in the case of malicious adversaries, we can actually improve the running time if we allow 1 more computational part, computing part. So if we have 4 PC with 1 corruption, we can improve in the running times. And that's essentially using the Fantastic 4 protocol from Dowsley et al. From Unix 21. So we have run the experiments with both like 3 PC for malicious and 4 PC for malicious. Okay, so what are we doing here? So just recapping, we are considered like result source computation setting. So the data owners need to share the data to the computing parts, and then they'll do some computations, and the final value will be revealed later on by reconstructing the secret shares. But here we are explaining between, I mean, we are considering that first we are trying to do some feature selection, then the model training, and we will be focused on the feature selection part of it. So what is this scheme that I mentioned that it's used a lot for semi-honest adversaries, the PPC from Rappe et al. It's essentially like, okay, yesterday I was talking about additive secret sharings, right? How you use them and to do computations. But actually you can do much better if you, instead of using additive secret sharings, use replicated secret sharings. For this setting where you have 3 compute parts and 1 corruption, or 1 semi-honest corruption at most. So what is the idea here? I mean, if you want to secret share some value X, as before, you pick some 3 handle values X1, X2, and X3 that are completely random, only subject to the constraint that the sum of them is equal to X modulo Q, the size of the ring that you're working on. But then instead of only giving 1 share, 1 of these 3 shares to each part, you're actually giving 2. So you give to Alice X1 and X2, then to Bob you give X2 and X3, and to Charlie you can give X3 and X1. What is the cool thing about it? I mean, now we don't, I mean, the scenario that I was presenting yesterday, we have this guarantee that no proper subset of the parts can heap over the original value, can learn any information about the original value, right? Here, that's not the case anymore. If Alice and Bob collaborate here, for instance, then they have all the shares. Alice has X1 and X2, and then Bob has X3, so they can put all together and heap over the full value X, right? But we have this still like this nice property that no single part can learn any information about X, just given whatever they have in terms of shares. So if you see Alice, she don't have the X3, and the X3 is completely random, subject to this constraint here, so no information about X. The same for Bob and Charlie. Okay, how can you do the basic operations? I mean, like in the underlying MPC scheme here, I mean, addition is still very easy, right? You can do it locally. So if you have two values that are shared in a format of replicated secret share, I mean, if you have X and Y, shares of X and Y, then to compute the sum of X and Y, I mean, Alice can just pick her shares X1 and sum with Y1 and X2, Y2, and Charlie and Bob do the same. They pick the coordinates of X and Y that have the shares of X and Y that have the same coordinates, and just sum log, right? So addition in general is very easy to do. And as before, in the case, as it was in the case of additive secret sharing, the replicated secret share scenario, you also can do very easily, like addition of a constant or multiplication by a constant. But if you remember from yesterday, the operation that was more costly and we had to do some tricks was the multiplication of secret share values. And we are using this multiplication triples. But here, that is a cool thing here. And it's the main advantage of replicated secret share. Replicated secret share essentially allows you to do one level of multiplication kind of directly. I will show you what is happening here very efficiently. So, okay, let's say that we have these two values here that are secret share X and Y, and we want to multiply X and Y without releasing any information about any of them. So what is the computation that we are trying to do is this one in the bottom here. If we express in the mathematical breakdown of the terms, and you end up with 9 factors here, right? X1, Y1 plus X1 and Y2 and so on. But the nice thing here, if you pick all these terms that only involve things with index 1 and 2, they can be locally computed by Alice, right? These 3 ones here, and this one as well, Alice could compute locally. But, okay, there are 3 here that Alice can compute. If you pick the ones that only involve the terms with index 2 and 3, they can be locally computed by Bob. And for the ones that have index 1 and 3, they can be locally computed by Sharp. So if you look at it, like all the 9 terms of this addition, they can be locally computed by one of the 3 parts. Some of them, they can be computed by either, like, if you pick like X2, Y2, it can be computed by either Alice or Bob. So you just attribute to one of them. But the main thing, like all these terms here, they can be locally computed by one of their parts. Okay, so let's say that they do the computation in that way. They do local computation. So Alice computes Z1, which is 3 terms of that original sum. Bob does the same with 3 other terms on Charm the same. But look, now, okay, they have computed one level of multiplication without doing any kind of interaction, right? But the main thing here is that they don't have replicated secret shares anymore. They have additive secret shares. So they did kind of for free one level of multiplication, but by change from additive secret sharing, from replicated secret sharing to additive secret sharing. So if they want to do like another level of multiplication, they will not be able to use this trick anymore if they don't do something about it. And what is this something about it that they are going to do? Is the following. They want to convert back from this additive secret sharing to the replicated one. And how is that going to happen? I mean, if you look at this secret share Z here, it's additive secret share of X times Y. The correctness is fine. They just need to convert back to the replicated secret share representation. And the idea here, if they don't want to leak any information, what they will normally do is the following. So they will compute a secret sharing of 0, of the value 0. And this can be done very efficiently by using PRF. So you have PRF where the keys are shared among some parts, and you can compute shares of 0. And the main thing here, they will pick some share of 0, and then they will sum this share of 0 with the shares of Z that they had, so that they will obtain some shares U, such that U1 plus U2 plus U3, it's equal to X times Y, but it has been randomized by these shares of the 0. And now what they do is the following. So we want to go back to the replicated secret share 1. So in the replicated secret share 1, Alice should have U1 and U2. So Bob will just forward to her the value of U2. Likewise, Alice will forward U1 to Charlie, and Charlie will forward U3 to Bob. So essentially, to convert back from the additive secret sharing to the replicated one, you need one round of communication where there will be 3 group elements that will be exchanged by the parts. Every part sending one group element and receiving one. But then you are back to this replicated secret sharing, right? So that's the underlying MPC thing that we use, and it's used quite a lot in the PPML solutions based on MPC. Okay, and this is for the same honest adversaries. If we want to have security against active adversaries, so malicious adversaries, essentially what we want to do is there are some techniques that you use, that you put some message authentication code to prevent the parts from deviating from the protocol specification. So we
have a question here.
Yeah. Oh, sorry.
On the previous, in the passive case, did you mention now how you get this multiplication result back to the replicated secret sharing?
How do I get the additive from the additive?
I understood that you can create a replicated secret sharing of 0.
Oh.
On the previous slide, I understood that you get replicated secret sharing of 0, but what does it have to do with the multiplication result?
I mean, so the multiplication result will be the Z here that you're computing. I mean, so if you look at the multiplication here, if you want to multiply X and Y, the term that you need to compute is this one in the lower side here, right? And the main thing is that this will consist of 9 terms, and that will be, I mean, for every one of these 9 terms, there will be one part that can compute the term locally. So they do the computation in this way, like, so let's say that 3 of the terms will be computed by Alice locally, the same by Bob and.
Yes, it's clear, but then you have full threshold sharing.
Then you have an additive secret sharing.
Yes, okay, full threshold. But then how do you go back to the replicated?
So that's the main thing. You first you add the share of the 0 to do the randomization, and then you exchange the message here.
Okay. Okay. You add the. Okay.
Yeah. So U will be the result of Z plus some shares of 0. I should have wrote down more details here. Sorry. So U will be Z plus some sharing of 0, and then you just exchange these shares here to go back to the replicated one. And then you can continue with the new level of multiplication gates, right? Okay, so if you want to do a protocol secure against malicious adversaries, then normally what you do with the previous technique, you add some message authentication codes so that no part can deviate from the protocol specification. So on top of doing the computations on the secret shares themselves, you need to do some computations on the max, but that's fine. But actually, that is a much more efficient way to do secure protocols for this case if you allow one additional computing part. So if you are in the setting where you have 4 computing parts and still the corruption threshold is only 1, then you can improve things by using these techniques from the Fantastic 4 paper, for instance, from Unix 21. So now we have Alice, Charles, Bob, and Donald, and at most one of them is corrupt. So we are again using some kind of replicated secret share here. But now every part is receiving, I mean, you're secret sharing X by creating like 4 shares that add to X. And you are giving 3 of them to each of the parts. So you give all, for part A, I, you give all the values except I minus 1 rule 4. Okay, so I'll not enter the details of this fantastic protocol, but the main trick that it allows us to do, like when you move to 4 computing parts, is the following. So that is a protocol that essentially allow you to jointly send a message, jointly pass a message. So you have this nice protocol where 2 parts can send a message to 2 parts that note some value. They can send a message to another one in a kind of reliable way in the following sense. Let's say that Alice and Bob are trying to send this message that they know, the value U to Charlie. And if by the end of the transmission, the 3 of them might agree, okay, the transmission was successful. Everybody agrees that all parts follow the protocol execution for that message transmission. But there is a nice property here that was developed in this fantastic flow protocol. It's essentially the following. If there is some problem in this message passing, if let's say like Alice send one value and Bob send a different value, and they pretend that they are sending the same value, essentially there is a detection mechanism that allows you to pinpoint 2 parts, and out of these 2 parts, one of them is the corrupt one. Sometimes this pinpointing mechanism allows you to pinpoint exactly 1 part, and then you already know, okay, this is the malicious guy. Other times it will just give you 2, and one out of the 2 it's the malicious one, but you're not guaranteed which one of them. So let's say that something went wrong, and you realize, okay, either Charlie or Bob's the corrupt part. But we are in the scenario where we have 4 computing parts, and at most one of them is corrupt. So what do we know here? We essentially know for sure that Alice and Donald are fine to go, right? We discovered something. So normally in this fantastic 4 kind of scenario, what they do is they follow. If some problem happens, you pick one. I mean, 1 or 2 parts will be identified as the possible malicious one. You pick one of them and exclude from the protocol, and then you convert this replicated secret share that you have with 4 parts back to the one with 3 parts only. And you continue the execution. Let's say that you excluded Bob. You don't know if Bob or Charlie is the malicious one. Exclude Bob, and you move to the replicated secret share with 3 parts only, and you continue the protocol execution by using the IACR protocol. And now, if some problem happens here, okay, you knew beforehand that either Bob or Charlie was the malicious one. So if some problem happens, still in this scenario with only 3 computer parts, then you are sure that Charlie is the one that is the malicious one. So what do you do? If no problem happens, then you continue with the 3PC1 solution and you finish things up. Otherwise, if some problem happens, exclude Charlie, and you move to the scenario with 2 computing parts only Alice and Donald. But back then, okay, if you realize that Charlie was the one that was actually malicious, then you can do the computation with these 2 parts doing the computation, but you can bring Bob back to kind of be the trusted initializer. Bob will be the one generating multiplication triples for this kind of 2PC computation. So that's essentially like how Fantastic 4 underlying MPC scheme works. In the case that we are going for malicious adversaries.
So these are the silence.
Silence and not silence. Yeah.
Good.
What were the security guarantees of the 3-party computation protocol which you use here after excluding a party?
After excluding the part?
Yeah, after excluding one party, you continue with the 3-party computation on replicated secret sharing. What security guarantees did you have there? Do you have active security in the support in that?
So essentially, you are not completely sure if Charlie is the malicious one, right? So that's the main constraint there.
Yeah.
And then you move to, shall we stop or not?
I think it's 5, and that means that now exactly is the time of Warsaw Uprising time when it started, and all the cars are standing and honking, so I think it's fine.
So there is no danger, okay? We are absolutely fine.
So maybe we should make a silence for maybe not the full minute.
I guess maybe.
Okay, good. Okay, but essentially, I'm not delving into the details of task 4 here, but it's essentially you move to this representation with complicated secret shares with 3 only, and you're kind of trying, you're hoping that you excluded the right person, but if you don't exclude the right person, you're essentially guaranteed that if some problem is still happening and if someone is blocking the computation, then you know who to exclude next and move to the 2PC. But I'm not into the technical details. I don't have the slides here. It will be.
Yeah, but certainly this requires that also in the three-party computation you can detect that something went wrong.
Yes. There are technical details there. I don't have the slides here. I mean, it would be impossible for me to explain.
Follow-up question would be, why don't you just from the beginning of the 4-party computation, immediately exclude one party and start doing a 3-party computation. And then if something goes wrong, you just exclude a different party instead.
I don't think you can prove the security of something like that. I mean, I'm not the one designing this underlying MPC scheme, but I mean, if you can design a scheme like that, that you can prove that secure, then I'd be happy to use it. I mean, it's about proving the security of the underlying MPC, right? I mean,
yeah, I mean, like if we already have this 3-party computation solution, which is actively secure, and apparently,
but it's more inefficient.
The 4-party computation, you say, is more efficient.
It's more efficient.
Yes, yeah, that makes sense.
So essentially, if you move like from 3PC with semi-honest up to 3PC with malicious, you are paying in general something close to 1 order of magnitude for that move. If you move from the 3PC honest to the 4PC with malicious, the price that you are paying is only a factor 2, more or less. So you have a big improvement in terms of efficiency. So that's why they do this move. Okay, yeah, but sorry, I don't have all the details of the underlying protocol here. It would be hard to follow if I try to just orally explain the details. Okay. Sorry.
Me, I would also like to ask one question. Going back to the slide where just before the Bob was excluded, when the 2 U's from Alice and from Bob are transferred to the Charlie, do they communicate in any way? What should they send to Charlie? I mean, is it a fixed? Because we know that Alice and Bob ought to share the same 2 XI shares. So do they sum them up and then send to the Charlie, and that's what they? Yeah.
So essentially, I mean, as we are doing computations with these replicated secret shares, at some point, these messages that they are normally sending these underlying protocols, they are based on shares that they both hold in common. So that, if you look at the shares here, some of the shares, they will be common among these parts, right? So normally this kind of message that they do, sending using this joint message passing protocol, are based on the shares that they jointly hold.
Right.
But then you are trying to detect if they are being like, they are sending reliable messages somehow.
Right, and honest workflow of this 4-party computation, we always want the 2 U's to be the same, right? And if they are not, then we raise the alarm, something is wrong, one of them is probably malicious.
That will be in the underlying MPC scheme, there will be a message being among all set of 2 parts being sent to other messages. It's not the case that only these two will be sent messages. There will be messages among all pairs, going all pairs to some others. I mean, I was just trying to give the high-level idea here. I don't have the details in the slides.
Okay.
But you can check the fantastic paper. It's a really great result. If you're trying to implement like PPML stuff based on MPC, it's a great underlying scheme for you to use. I totally recommend you to read the user paper.
Okay, thank you.
Okay, so this the highlight idea is therefore you have this 4PC scheme where if everything go right, you do the computations with 4 parts. If problems happen, maybe it will move to a 3PC, 2PC, but you still keep the efficiency. So that's the main message here. And that's the underlying scheme that we use for 4PC computation with one option. But of course, we also want to use some building blocks for some operations that are appearing all the time, such as secure comparison or secure arguing. So arguing, you have a vector, you want to find the index of the smallest value in the vector, and you want to obtain a secret share of the index of this minimum value. Also, like a quality protocol, and secure division, all these kind of things. And we didn't design our own protocols for this. There are existing protocols for this kind of things that we just use. And I will not get into the details yet. Okay, so how did we do this feature selection in a secure way? So essentially, we had a protocol for computing the scores of every feature and a protocol for doing the filter part. So let me first talk a little bit about the filter part of the process. Okay, so the input that we have some data matrix where the size of the matrix is M, the number of instances that you have, times P, which is the original number of features that you have. And then somehow you would have computed the score of every feature there. So you have P scores for the features. And in the case of all protocol, we also need some upper bound on the value of the score. So we need some upper bound T on the value of the score. And that's not a strong assumption because normally these scores, a lot of times there will be some numbers between 0 and 1. For instance, in the original gene input, it will be between 0 and 1, right? So you just pick T, the upper bound as being 1, and you are fine. And why do we need this upper bound will become clear when we go over the code here. Okay, and the output that we want after this filter part of the protocol, we want to obtain some matrix G prime, which again will have a size, the number of rows will still be M, the number of instances that you have. But now you only have K columns. So you selected only some of the features. And this G prime will be the matrix containing all samples, but only the features that you selected. So how do you do the filter part? Is actually quite straightforward. I mean, what you are doing, you are doing a loop for K times to select the K columns with the smallest gene scores. And every time you enter this loop, you need to select the index of the minimum value that you have with a gene score of the remaining ones. If you already use the feature, then you are not picking the feature again. So you essentially use this secure arguing protocol to compute a secret share of the minimum, the index of the minimum. And then what you do, you essentially use this value of the result of the arguing in order to create a one-hot encoding of the selected index. So one-hot encode, it's an encoding that will have, it's a vector of zeros on 1, and you have zeros in all positions except one position, which is 1, and indicates the value that you have. So how you do that is essentially you're computing this secure equality test here in between with the result of the argument and the value, the loop. I mean, you're looping over all possible features, and if the result of the argument is the feature that you are checking now, if they're the same, then you know that the feature that you need to put in that position is that one. So you just put this flag here, and then you create this one hot encode in the matrix T. But again, as I mentioned, you shouldn't be picking the same feature over and over again, and that's why we need that upper bound T. So what you are doing here, if you pick some feature in this iteration of the loop, essentially you are doing this oblivious update of the value of the score of that feature. You are moving it to, instead of being something very small, be equal to T, which is an upper bound on your scores. So you are guaranteed that whenever you enter another interaction of this outer loop, outer for loop, you are not selecting that feature again. Okay, and so it's quite simple protocol. And then in the end, what do you do? Essentially, you do some secure matrix multiplication here. I mean, you have this the input matrix, which have all the features, all the instance, and then you multiply by this one hot encode of the features that you selected in order to get the matrix D prime, which only have the columns that correspond to the features that you select. So, for instance, I mean, let's say that the input matrix was this matrix here, and we had that the Gini scores were given by G with 6, 5, 26, 83, and 14. Then the one with the lowest score would be the last one, right? So what would happen when you generate this one hot encode? Like in the first column here, you would have zeros except for the last position. That shouldn't have happened. Okay, so essentially you have a bunch of zeros and in the fourth position one. And after you exclude the 14, the smallest score there is then the 26. Then the 26, second position. So in the second column you have zeros except second row, which is 1. And then you do just this multiplication and you're selecting the columns, the features that you pick up, right? So that's how you do the future part. It's a very basic protocol. And you, of course, you're trying to optimize all this secure comparison, multiplications, all this kind of stuff. But the main thing is now, how do we compute these scores? I mean, there are different methods for computing the scores, and the most efficient one that we have is the Gini one. Yeah.
Can I get the mic? Sure. Yeah, so I have a question to the algorithm, because what I understand is like you pick the k lowest feature, the k lowest values of the vector, right? Sorry. You pick k lowest values of the vector, right?
So you're trying to select out of the p features that you have. You are trying to select indices, k of the
k indices of the feature vector, right?
K of the features. The ones with the best scores.
Yes, it's based on the vector G.
Yeah, the scores of the features.
Yeah, so why is that so complex? Because here you have the private operation argument on the vector, and you get the index from it. So why don't like remove this value of from the vector G and then recompute it?
But how can you remove it without leaking which value you selected? So that's why we have to do all of this in an oblivious way. So, I mean, when you are doing secure computation in MPC, normally you have to, I mean, you have to replace like conditional operations with multiplications, oblivious stuff a lot of times.
Yeah, but
so you cannot just review which value you selected and then say, oh, let's exclude this value.
Okay. Yeah.
So you essentially are doing that, but in an oblivious way, you are picking this value, and then you say, okay, if this value that we selected here is the fourth one, whenever we run this for loop here for j equals to 4, then this line here will be activated, and we'll send this value. We'll update the score in that position to be equals to t. It's the upper bound that we have. Otherwise, you would have to somehow mark, okay, I'm not using the fourth position more, but then you are leaking this information to everybody. Or exactly what we don't want to do.
Yeah, exactly. Makes sense. It makes sense.
Okay, so that's for the filter part, and then let's move on to see how we do compute the scores for every feature. I mean, let me briefly mention that in case that this data was partitioned in a vertical way, so every feature is held by some of the parts. If it was partitioned on that way, and also the labels were available to all the parts, then actually the computation of the scores of the feature will become trivial, right? So, for each score, for each feature, there will be one part that hold all the values for that feature and hold the labels as well, so it can compute the scores of that feature. But that's a quite strong assumption in general, so we are not look at this scenario, not because of the training data be vertically partitioned, that's not strong assumption, but assuming that all the parts also have access to the labels is quite strong. If that's your setting, you can improve, you can do like the score computation in the essentially locally, so you improve. There will be a big improvement in the overall running time of the feature selection. But in general, you cannot do this kind of assumption. So you need to compute the feature scores in a private way as well. So what we are going to do here, for every feature, you pick the threshold that we use to split as mean the mean value of, you pick all the training samples that you have, you compute the mean value, and use that mean value as the split point. So in the clear, the gene input method that is normally used, you sort all the feature values, and then you try for every possible split point, and you compute what would be the gene input if you do the splitting there, and then you pick the optimal one. Which there are two things that will become more expensive if you are trying to do that in a secure way. The first thing, sorting to begin with, it's expensive if you're doing a secure way. And secondly, you are trying to do the splitting in every possible point. So you're repeating the operation. You're doing one additional for loop there, which kind of make a big improvement in part. So we are doing this mean split point Gini idea. Okay, so what we are doing here, okay, so we pick the threshold theta as being the mean value of the feature, and then we define two sets. So there will be the set S is smaller than or equal to theta, and the set S bigger than theta, and it will essentially denote the samples that have that feature bigger than or smaller than the threshold that we are computing. And then we also define some partition of the data set according to the labels. So for every possible class C, we have LC as being the set of samples for which the label is C. And then essentially to compute the Gini input of this, we can compute the probability of C, probability of the class being C, if that specific feature is smaller than or equal to theta. It's essentially the cardinality of this intersection between S is smaller than or equal to theta with LC divided by the cardinality of S is smaller than or equal to theta. In a similar way, you can compute the probability of the class C, given that the sample has a value bigger than theta for that feature. Okay, and then the Gini input will become this expression here. So the Gini input of this set of the partition will be given by 1 minus the sum over all classes of P of C being bigger than theta to the square. In a similar way, you can define for for the one of B is smaller than or equal to theta, and the one being bigger than theta. Sorry. And then essentially like the gene input of the feature in general, it's the weighted average of these two values here. So essentially you have to compute this expression here, which is 1 divided by m, the size of the set, versus times the gene input of that set, plus the size of the other one, times the gene input of it. Okay, so how do we do that in a secure way? We have a protocol for that as well. So essentially what we have here, as input, we have secret shares of some column. So we have some feature, we have for all samples, the values of that feature. So we have essentially one column of the original data set. And then we have secret shares of one hot encoded version of the label. So we're assuming that somehow whoever gives the labels is giving us already in one hot encoded format, or otherwise we would have to translate from the original format to one hot encoded. Okay, and as the output, we'll try to generate the secret share of the score of that feature there. So how do we do that? Essentially, the first thing we are using the mean as the split point, so we just compute the mean value. It's essentially just summing all the values in a secret share way and then multiplying by the inverse of the number of samples that we have. Okay. And then we will have a for loop here, which essentially we are trying to compute these values here. We want to, by the end of this for loop here, we want to be in such a position that we'll have secret shares of all these values here, such that A will be the size of the set S of samples that are smaller than, that for that specific feature have values smaller than or equal to theta. Then B, the ones that are for that feature are bigger than theta. Then vector A of j is the ones that have the feature is more than or equal to theta on a part of class J, the J class in the label, and a similar way for B in relation to the ones that have the feature value bigger than theta. Okay, so what we do essentially we initialize all of these with zeros, of course, and then in here, like in line 4, we are doing some secure comparison in order to determine if this instance that we will go over a for loop over all the instances. And for every instance, we need to determine if this instance is from S bigger than theta or S equal to or smaller than theta. So we determine if that's bigger than theta 1 for the feature value. If it is, then the value B is the one that will have the size of this set, so we just update the value of B, right? But the value of the set A, the sample, this number of samples that have that feature value is more than or equal to theta, then we update in an indirect way to save on efficiency here. Okay, but then we also have to check, okay, given that it's part of this set here, the set of samples that have this feature value bigger than theta, which class it belongs to? So how do we do that kind of check in an oblivious way? So essentially we are doing that by using this multiplication here. We are multiplying to check if it's part of this set here. We are multiplying the flag that says that it's part of the set S times the one hot encoding. And then we get a flag that indicates if it's part of this intersection of S bigger than theta with LJ. And if that's the case, then we can just increment the value of the relevant. Sorry, it should be still here. The relevant value of BJ, because then we know, okay, that has a feature value bigger than theta, and it's from class J. So yeah, let's increase this value here. And for increasing the value of A of j, we are actually doing that in an indirect way to save on a little bit on the costs. Given that we already computed all these flags, we don't have to redo all the computations. Sorry. Okay, so Okay, one optimization that we are doing here, we are for the last class, instead of doing the computations inside here, we just have the fact that the sum of the vector capital A over all values should be equal to A, so we compute in an indirect way. And you can figure that that's a small optimization, but well, if it's a problem that where you only have like 2 classes, you are saving a lot. Or if you only have few classes, that's saving a lot. You just big for loop. Okay, so in the end of this, when we are done with these lines 2 to 14, what we get is that we have counters that are secret share and store these values here. And then we want to compute the gene score. And the gene score, like the expression that we had beforehand, it will essentially be this expression here, where, I mean, you can manipulate the mathematical terms, and you end up with this 1 divided by m times this expression in the brackets here, which is a minus 1 divided by a, the dot product of the matrix A with itself, and then similar expression for the b's, right? So essentially what we are doing, you need to do here, you need to compute some inner products of A with itself, of B with itself, then you need to do some secure division by the value of small a and by small b. And then in principle, you need to do like a division by the value of n. But do you really want to do this additional division? Not really, because I mean, this division by n don't affect the relative order of the score. So you can avoid doing that division by just like, instead of having the values being between 0 and 1, now you have the values being between 0 and n. And then the upper bound that you use for the filter protocol, you increase from 1 to n. And then you avoid one additional division here. Okay, so we have implemented this, and I mean, this.
Sorry. Can't you avoid the inner for loop with just arg? Sorry, can you avoid the inner for loop with argmax and matrix multiplication, basically, as you assume that every sample has only one label, if I understand correctly?
So you're trying to do argmax where? Yeah.
Because basically you are iterating in the inner loop for every class for the sample I, yeah? And you are...
So you're trying to do some argmax instead of doing this?
Yeah.
I mean, I have to see the write down protocol. Probably you can do something in that line. I don't think it will save you much because the cost of the argmax will be very much. Okay,
you haven't checked that.
My without check intuition is that you wouldn't save much using argmax because of the cost of the protocol will be equivalent to this thing here.
Okay,
probably. I mean, to be sure, you have to write down proof things, but probably can work something in that lines. Yes. Okay, so we have implemented this, benchmark this on Azure with 3 or 4 collocated machines. Essentially 32 cores, 64 gigabytes of memory. And the running times that we have here, it's essentially including communication time. So it's not only computation time, but also the delay due to the communications. So you can run, I mean, we run for some data sets. You can do in reasonable time. And I mean, to compare with the original gene method, we have done the same thing, but with the original gene index time, which requires you to do the sorting and then all these split computations, right? And essentially you save like 1 order of magnitude in all scenarios. I mean, as I was mentioned before, like if you pick like passive 3PC, and you move to the active PPC, you have some performance loss, which can be improved if instead of using only 3 parts in the case of malicious adversaries, use 4 1. Essentially, like active 4PC scenario, the running times are less than twice the running time of passive 3PC. But if you compare like doing this mean split Gini with doing the standard Gini for the computation of the scores, then if you pick any column here, you compare to here, it's essentially like 1 order of magnitude gap. So like this simple, change that in the clear don't have any significance at all. You know, like it will not improve your running time in the clear, pretty much nothing. And in secure ways, it makes a huge difference in computation time. On the accuracy level that you can achieve for many data sets is actually the same. Okay, so to finish up, I will briefly talk about something that use related method, but I'll just talk in high level. Which is decision trees. So you hear a lot about the training and the inference of neural networks, but I mean, a lot of times if you have a like kind of structured information decision tree or decision tree assemble methods, they can be very good. And they are deployed a lot in machine learning algorithms as well. So are there solutions out there? So that was the question. There are solutions already, like for if you consider a case like discrete features, so you are trying to compute some ID tree kind of trees using genetics. Again, why are we using genetics for the training of the trees? For this insecure way, which was resolved by the Hogg et al. In 14. Because gene index as splitting for computer splittings, they are much more MPC friendly than using splits for decision trees with something like multiple information. So even though like decision trees in the clear, sometimes people do with gene index, sometimes with multiple information. If you're trying to do this in a secure way, gene index is normally much better for performance reasons. But okay, so we have this for discrete features. But I mean, real life features are often real numbers, right? So what would we do if we have like, we want to train some kind of decision tree assemble kind of method or a simple decision tree or decision tree assemble? But our inputs are the real numbers. What should we do? There was not much on this direction, MPC-based solutions until very recently. I mean, okay, so if you consider like the problem in the clear, so how do you do training of decision trees with continuous values in the tree, in the clear? Normally what you do, you sort the training examples for each feature, and you try to find the optimal cut point of the features. And then on top of it, you don't do that one single time for the tree, you do that for every single node. So if you try to run that thing on top of secure MPC or the secure solutions, that would be like very, very costly because you have to do the oblivious sorting for every single node and then try to test all the splitting points in an oblivious way and determine which one is the best. Not very efficient. Okay, so secure sort is expensive. We want to try to avoid it. So what can we do if we don't want to use something like in the lines of decision trees or random forest, something in that line in a secure solutions? Okay, so shall we do discretization to begin with and then run some protocol that is based on discrete values? Maybe that's the best, right? Another thing, like whenever you are running the train of decision trees in the clear, how big should you allow the trees to be? I mean, in the clear, that don't make any big difference, right? You can allow trees to go have a big depth, but if you are doing like a decision tree training in a secure way, essentially the depth will have a big impact on your running time. So is it better to have one single tree of big depth, or would you prefer to have many trees that have a small depth? Sometimes even a depth of only one. So So you have like decision stumps instead of having big decision trees with big depth. So all these kind of trade-offs, whenever you are trying to use these methods in secure solutions, you have to consider. And I mean, these things that in the clear don't matter really. They make a huge difference whenever you are in the PPML context. So okay, so maybe we want to train some random forest. So what is a random forest? It's essentially a decision tree ensemble where you have many trees and use this. I mean, this group of trees to make your decisions. I mean, you classify your new instance according to every single tree, and then you do some majority voting. Well, many times, like this tree here will not output a single class, but it will output some distribution, probability distribution over the class, and then you do some voting mechanism here in the end to find the final class that you want to output, right? Okay, so I mean, if you want to run something like random forest, then you have to support the kind of techniques that are used for random forest. Like you have to support like bagging, which is like you're bootstrapping your training data. So for every single one of these decision trees, instead of, I mean, if you just use your same training data for every decision tree, you end up with the same decision tree, right? So it doesn't make any sense to make a lot of decision trees with this same data set. So normally what you do, for every one of these trees, you pick random samples from your training samples with replacement normally. And also, like a good practice that's used in random forest is that for every like tree, you don't use all the features. You only use a subset of the features, the so-called subspace sampling technique. So, I mean, and you combine these two techniques so that every tree kind of differs from each other. So when you combine the set of trees that are a little bit different from each other, then you get a more reliable, more robust classifier. Okay, so if you are doing this in a secure way, you want to avoid as much as possible security sorting. And what are the alternatives that we have to avoid the security sorting and do something that's competitive in terms of accuracy? Some things that we showed up that can be done, like one possibility that you have, like you can do secure discretization of the data to begin with. And then on this discrete data, you run the decision tree training for discrete data that you already have. That's one option that can work. Another thing that you can do, like you can combine secure discretization of the data, followed up by secure training of random forests. So instead of training one single tree that maybe needs to go deeper to have a high accuracy, you train many trees that can be of lower depth. And but actually there is one idea there that it's sometimes used in the clear. When you look at it in the context of secure solutions, it can be very efficient, which is the idea of extra trees, or they are so-called extremely randomized trees. So what are extremely randomized trees? So you pick these trees, and you're not trying to do discretization or computing optimal split points. You know what? You pick, like for every tree, you pick a random, completely random split points. You don't care. You just insert more randomization in the model, and you train a lot of trees, and in every single one of these trees, the split points will be picking for each feature. They will be picking at random. I mean, normally you want them to be in the feature range. So you normally pick, you determine what is the maximum value of the feature, the minimum value of the feature, and then you pick a random number in between the minimum and the maximum, and you use that as the split point. And it turns out that that's, I mean, the extra trees or extremely randomized trees, they are competitive methodically. And whenever you are doing this in a secure way, this saves you a lot, because now you don't have to do secure discretization anymore. You're just training a lot of trees that can be of lower depth and using handle split points. Yeah, so I mean, you can check the details in the PETS paper. I will not have time to go over it. But essentially what we did there, it's we use secret share solutions again. I mean, in MPC, sometimes computations are more efficient if they are done in arithmetic format. Sometimes in binary format, things like secure comparison, they are normally more efficient to run in binary format representation. So we use both and then do conversions among them. And then we have to optimize some of the secure comparison and the quality tests to circumvent. I mean, you normally, a lot of the secure comparison protocols, they do a full bit decomposition. So they essentially transform from the arithmetic representation to binary representation by doing a full bit decomposition, and then they do some operations on this binary representation. But we show that in the context that we are, we can essentially avoid the full-blown bit decomposition and just do part of the computation that is normally done for the bit decomposition. And essentially, we are doing like equal width binning for the ones that we are doing discretization. So we assume that the binnings, they are the same size, and maybe some of the binnings will get more elements, others will get less, and so on. And that essentially involves some secure protocol to find the minimum and the maximum, and then you can split the points. You can use like equal width to split the points. Okay, and for the secure discretization, the solution that we have there, we just put some one-hot encoding of the bin, then we can run the old protocol by the whole. If you're interested in the details, please take a look at the PETS paper, and we can do the sampling in a completely preserving way. Okay, and my final slide here. So, I mean, we were talking about security training, secure inference, all this kind of things, but if we really want to deploy some large-scale framework for privacy-preserved machine learning, we need to get something that's end-to-end, that covers all the ML pipeline. So there are many open problems there. Like, if you're interested, try to look at, I mean, of course, secure training, secure inference is important, but try to look also at this, how to do the pre-processing in a secure way, how to do the fine-tuning in a secure way, how can you pick hyperparameters in a secure way. All these kind of operations, if you want to deploy these things, they are very important for the ML pipeline. That was it.